Hello friends, welcome to UGC EPG Pathshala program. I am Aditi, Assistant Professor, Department of Geography, Swami Shraddhanand College, University of Delhi. And today we are going to learn about water balance and drought. The water dynamics like occurrences, amount and circulation on earth have been always of interest to mankind. As we know that our climate system is largely regulated by the global energy and water balance and the spatial and temporal variation which involves the flow of energy and water within the climate system and their exchanges with outer space and the surface. Historically, the overall picture and details about the water balance was first marked by Copernicus in 1543. He had calculated the mass balance of the solar system and considering the revolution of cosmic bodies. In the present scenario, the water balance of Earth extended immensely importance due to lack of drinking water, deteriorating water quality and declining water resources and groundwater table. We all are experiencing negative impacts of changing weather conditions, and on some extent we are also responsible for these unwanted changes. Various studies are going on global circulation of water to evaluate the severity of currently perceived water crisis situation and predictions and consequences of climate change. The hydrological cycle forms the most dynamic part of the overall water circulation of Earth. While it is the most important water cycle in our daily life, other water cycles which operate on geological time scales are also important in visualizing a complete water perspective of our planet. Concept of water balance. The word water balance was first of all used in 1944 by the famous meteorological and climate scholar C. Warren Thornthwaite, who meant that it is a balance between precipitation, water obtained by melting of snow and evaporation, groundwater recharging and surface flow of water. The Earth's water budget is driven by precipitation and evaporation. Air temperature, precipitation, soil moisture and evapotranspiration are realized through the balance of incoming and outgoing energy in combination with water at Earth's surface. The incoming energy direct towards the surface is comprised of shortwave radiation from the sun and longwave radiation from the atmosphere. The outgoing energy from the Earth's surface is comprised of long wave radiation and heat that is associated with latent heat and sensible heat. Similarly, the water balance is the ratio between water inflow and outflow estimated for different space and time scale for the Earth as a whole, for ocean, continents, countries, natural economic regions and river basins for a long term period as for particularly years and seasons. As we can see that the ocean and seas are having highest volume of water, on the other hand the volume of water in the atmosphere is much lower than ocean despite having large area. The residence period of oceans and groundwater is highest among all the water bodies, followed by ice caps and glaciers. Thus, ocean ground water and glaciers have important role in upholding water balance on Earth's surface. For each continent, evaporation is equal to the difference between precipitation runoff. The ratio of evaporation to runoff differs greatly on various continents. In Australia, the evaporation is close to precipitation. In all other continents except Africa, evaporation is less than about 66% of the sum of the precipitation. The amount of river runoff into the ocean from the land is approximately same as the amount of evaporation and precipitation from the ocean. For the individual ocean, evaporation is equal to the sum of the river runoff into it and horizontal transfer of water from other oceans through global oceans circulation process. For Atlantic Ocean, sum of precipitation and runoff is less than the magnitude of evaporation. On the other hand, in Africa, ocean evaporation is substantially smaller than the sum of precipitation and river runoff. The inflow of water vapor into the atmosphere from evaporation may be both larger and smaller in different latitude zones. The difference between precipitation and evaporation is equal to the difference between inflow of water vapor into the atmosphere and the outflow resulting from the horizontal air movement. The components of continents and ocean water balance are not constant and it changes as a result of climatic fluctuations and other factors. Studies have shown that in the 20th century, level of world ocean has increased by about 1.5 centimeter, which reserves of subsoil water on land and volume of water in many lakes have declined. Ocean has increased by about 15 centimeter with reserves of subsoil water on land and volume of water in many lakes have declined. Though sources of water contribution to rise in water level in world oceans are not absolutely clear, melting of ice covers, loss of groundwaters and decrease of water in lakes on land are responsible for increase in volume of oceanic water. Water balance of surface and subsurface. Water balance associated with determining spatial climate features, typical landscape, possible water management and land use precipitation, evaporation, river runoff and groundwater outflow not drained by river system are basic components of water balance. For the assessment of heat energy and water balance, accuracy in data on precipitation, evaporation and runoff is very important. Water balance equation for land surface may be given as precipitation equals to evaporation at earth, which is equal to the difference between evaporation and condensation at earth's surface plus surface runoff plus flow of moisture from earth's surface to deeper layers. Evaporation is one of the major process of transformation of solar energy at earth's surface and it is very much affects yearly runoff. Thus, runoff normal and coefficient of runoff are linked to principal components of energy balance. Average total evaporation from land surface depends on the quantity of precipitation and inflow of solar energy. Evaporation increase with increase in radiation balance. If soil is dry, total precipitation is caught by molecular forces on soil particles and eventually expends on evaporation. In such condition, runoff coefficient will be 0. Thus, the average dryness will rise with increase in radiation and decrease in precipitation. For sufficiently high value of the total precipitation and sufficiently small value of total inflow of radiation, a state of full moisturing of the upper layers of soil will be achieved. In such cases, the maximum portion of heat energy available from all sources will be expended on evaporation. The value of this expenditure may be calculated by considering the valve nature of the latent heat exchange between underlying surface and the atmosphere. Experimental studies have shown that turbulent heat conductivity of lower layers of atmosphere depends substantially on the direction of vertical turbulent heat flow. If the direction of this flow is from earth to atmosphere, values of turbulent heat flow become higher due to increased turbulent mixing. If direction of turbulent heat flow from atmosphere to earth, inverting temperature distribution reduces exchange intensity and turbulent heat flow becomes small. As a result of the valve effect, average turbulent heat moves from earth's surface to atmosphere in nearly all climatic zones of land. Yearly sum of turbulent heat flow are positive. Thus, air's turbulent heat flows cannot produce substantial inflow of energy to underlying surface, and heat expenditure on evaporation are compensated only by radiation balance. The magnitude of possible evaporation at a locality is determined by the radiation balance, which is different in conditions of sufficient and insufficient moisture. Now, the contribution of plants and vegetation in balancing water on the earth. Contribution of plants and vegetation in balancing water. The atmosphere receives a considerable amount of moisture through transpiration of plants, which usually represents several tenths% of total evaporation. Transpiration is the process by which moisture is carried through plants from roots to small pores on the undersides of leaves, where it changes to vapor and it is released to the atmosphere. It is found that about 10% of the moisture in the atmosphere is released by plants through transpiration. Remaining 90% come through evaporation from oceans and other water bodies. Therefore, transpiration may exert a considerable influence on the atmospheric water exchange. The molecules of water vapor of external origin and local origin are mixed in the atmosphere during turbulent exchange. Therefore, the ratio of total precipitation derived from external water vapor and derived from the local water vapor is equal. The precipitation in an area also depends on the plant cover, which influences the quantity of local evaporation. It has been observed that when mossy swamps are drained and a forest cover develops, in such areas total evaporation appears to increase. Reverse effects is observed when lowland grassy swamps are drained. The influence of evaporation on precipitation depends on the size of the area in which evaporation occurs. Soil water cycle. Evaporated water cools the earth as a whole, not only the local area of evaporation, but the evaporation of water from trees and lakes could have a cooling effect on the entire atmosphere. Vegetation influences both albedo of the earth and the amount of water vapor and the carbon dioxide in the air. All types of plants plays a role in both the water cycle and the earth energy balance. Plants also produce their own microweather by controlling the humidity and temperature of their immediate surrounding. In moist climate, especially warm and wet climates, the potential for evapotranspiration is very large, like equatorial region. Here, the valve of Bowen ratio is very small. In dry region, lack of water to evaporate leads to high Bowen ratio. The significance of the Bowen ratio is that it gives us an indication of the relative partitioning of net radiation of a region. Now, water balance of the atmosphere. At a particular price in the atmosphere, the water is brought by evaporation from the earth's surface and is removed by precipitation or air currents and horizontal turbulent exchange. The water balance equation for atmosphere is therefore obtained by summing all the categories of inflow and expenditure of moisture within a vertical column passing through the atmosphere and is given as E is equal to the precipitation plus quantity of moisture received or lost by vertical columns due to air currents and horizontal turbulent exchange plus change in quantity of water in the column. Now, the water balance of water bodies. The same equation which is used for surface water balance can be used for water balance of water bodies. Here, runoff will describe the local redistribution of water along the horizontal plane during the time interval under consideration both within the water body itself and in layers of underlying soil. Similarly, for a closed water body, it will also be equal to overall change in the water content both within the body of water itself and in underlying layers. In these cases, there will be perceptible change in moisture content. Contribution of local evaporation to local precipitation. The principal sources of water vapour for precipitation over continent is advective water vapour, which origins as ocean evaporation. The role of local evaporation is modest in total volume of precipitation, especially territories of dimension less than 1 million square kilometer. The indirect influence local evaporation on local precipitation derives from the linkages between the volume of precipitation and relative humidity of the atmosphere. Now, we will discuss the thermal differences between land and water. The continents heat up faster than the oceans and they cool down faster too. For example, London. London has an average January low temperature of 2 degrees centigrade, while Winnipeg is closer to minus 20 degrees centigrade, even though they are located at almost the same latitude. There are a few reasons for the land ocean cooling differences. The first is specific heat capacity. Water has a higher heat capacity than land, so it takes more heat to raise the temperature of 1 gram of water by 1 degree than it does to raise the temperature of land. 1 calorie of solar energy, any type of energy that will warm 1 gram of water by 1 degree centigrade, while the same calories would raise the temperature of a gram of granite by more than 5 degrees centigrade. The second is transparency. The heat observed by the ocean is spread out over a greater volume and extent. The heat can be dispersed over a greater depth in water. It depends on the level of transparency. The third one is evaporation. The ocean loses a lot of heat from evaporation, while there is some evaporation from wet soils and transpiration by plants. The land use does not have anywhere near as much available moisture to cool it down. The land surface energy and water balance are highly coupled by the partitioning of absorbed solar radiation into terrestrial radiation and the turbulent fluxes of sensible and latent heat, as well as the partitioning of precipitation into evaporation and runoff. Evaporation forms the critical link between these two balances. The fourth one is currents. The ocean can observe heat energy over a greater depth and spread that energy amount with their ocean currents and tides. The oceanic water moves in the form of ocean currents from equator to pole, pole bars, and from poles to equator. Currents have very important role in normalizing ocean temperature, but that not happen in the case of land. Soil water budget. In the soil water budget, soil moisture is important for plant growth. A lack of moisture content over a growing season is a good indicator of drought, which can have social, environment and economic impacts. Soil moisture deficit differences between rainfall and evapotranspiration vary across the country and from year to year, ranging from 0 to 500 millimeter. Soil moisture plays an important role in preventing or prolonging summer droughts. When the ground is wet, water evaporates as the day warms up. The warm, moist air rises until it encounters colder air high above the earth's surface, leading to afternoon rain showers. The water remains in the ground through the cool night and the cycle repeats the next day. The soil water budget is an accounting system for soil moisture using inputs of precipitation and output of evapotranspiration and gravitational water. It can be understood by following equation. Precipitation equals to equal actual evapotranspiration surplus plus storage. In arid and semi-arid region, water represents the main ecological constraint for plant survival, and hydrological process determine the direction of evolution and ecological functioning of soil vegetation system. Soil moisture dynamics are the center components of the hydrological cycle and are mainly determined by the process including infiltration, percolation, evaporation and root water uptake. Water movement in unsaturated soil is an inhomogeneous nonlinear process and is influenced by climatic and environmental factors such as precipitation, evaporation, vegetation and soil properties. The effect of vegetation on soil water movement strongly depends on vegetation types and density. As seen in the figure 4, the soil physical properties like soil texture, porosity, unsaturated flows, etc. have a profound influence on soil water movement. Increasing temperature and changes in rainfall patterns are expected to increase the frequency and intensity of drought in many regions. When rainfall is less than normal for several weeks, months or years, the flow of streams and river declines. Water levels in lakes and reservoirs fall and the depth of water in wells increases. If dry weather persists and water supply problems develop, the dry period can become a drought. The term drought can have different meaning to different people depending on how a water deficiency affects them. Drought is described in terms of various statistics that summarize drought duration, intensity and severity. Droughts are generally classified into 4 categories. First is meteorological drought. Meteorological drought refers to precipitation deficiency, possibly combination with increased potential evapotranspiration extending over a large and spanning extensive period of time. Now, soil moisture drought. Soil moisture drought is the second type of drought. It is a deficit of soil moisture mostly in the root zone, reducing the supply of moisture to vegetation. Soil moisture drought is also called agricultural drought because it is strongly linked to crop failure. Drought affected land. Hydrological drought. Hydrologic drought is broad term which is related to negative anomalies in surface and subsurface water. Examples are below normal groundwater levels or water levels in lakes, declining wetland areas and decreased river discharge. The next is socio-economic drought. Socio-economic drought is associated with the impact of three above mentioned types. It can refer to a failure of water resources system to meet water demands and to ecological or health related impacts of drought. An overview of the most important drought impact is provided in table 1. It can be noted that more types of drought impacts are related to hydrological drought than to meteorological drought. In figure 8, it has been depicted that the state of drought around the world in August 2015. The dark brown patches indicates area of exceptional drought, through to patches of dark blue showing areas of exceptionally wetness. Most of the African countries are worst affected by drought. A groundwater or hydrological drought typically refers to a period of decreased groundwater levels that varies regionally and locally based on due to differences in groundwater conditions and groundwater needs for humans and the environment. Reduced groundwater levels due to drought or increased pumping during droughts can result in decreased water levels and flows in lakes, streams and other water bodies. Decreased groundwater flows to surface water can affect aquatic ecosystem that rely on a continuous supply of groundwater to sustain aquatic habitats and stream flow. The groundwater has important role in keeping water balance on the earth. The fresh water found beneath the surface, which is beyond the soil root zone, is known as groundwater. It is the largest potential fresh water in the hydrological cycle. Groundwater level in most of the countries decreasing due to overconsumption. Groundwater systems are possible backup sources of water during periods of drought. Thank you.